Hello students, welcome to EPG Pathsala. I am Professor D. Vel Murugan, University Grants Commission Basic Scientific Research Faculty from Center of Advanced Study in Crystallography and Biophysics, University of Madras, Gindy Campus, Chennai. Today I am going to talk to you on the module dealing with X-ray anomalous scattering, Bijvoet difference and violation of Friedel's law, which come under the paper Biocrystallography. So students, let us see what we are going to learn in this module as objectives. First of all, I am going to tell you what I mean by resonance. Then I am going to explain to you what I mean by anomalous scattering. Then the Friedel's law. Then violation of Friedel's law. I am also going to explain to you what I mean by the Bijvoet difference and how this Bijvoet difference is going to be used to determine the absolute configuration of a molecule. Then I am going to teach you what do you mean by a difference Patterson. Then finally, I am also going to give you an algebraic proof of the Friedel's law. In physics, you must have learned about sound. There is an experiment with sonometer where you talk about a tuning fork which is already tuned a predetermined frequency. The length of the wire is kept in tension by rolling it over two pulleys and hanging it with a weight. Now, this vibrating string frequency can be made to vibrate with any frequency by keeping a movable platform over it and the string is passing over it. Now, we can have an external frequency with a tuning fork, and if the vibrating segment frequency generated matches with the frequency generated by the tuning fork, we hear a loud noise. At this stage, if we keep a thin paper rider on the string, it will be thrown away by the vibrating string. This is known as resonance, where the external frequency of vibration matches with the natural frequency of vibration of the object. We are now going to see what is anomalous scattering in X-ray crystallography, what is Friedel's law, and what do you mean by violation of Friedel's law. In X-ray diffraction experiments, when the frequency of the incident X-ray radiation is closer to the absorption frequency of an atom or the natural frequency of vibration of an atom in the molecule, the atomic scattering factor of that atom, instead of being a real quantity, now becomes a complex quantity. That is why you are calling it as anomalous, a strange. Usually atomic scattering factor is a real quantity. But in the case of this absorption rate frequency, atomic scattering factor little f becomes the normal scattering factor f naught plus a correction f prime in the real part, which is usually negative, plus I f double prime. So f double prime is a positive value. Now I is coming. So it's a complex quantity. So this is why it's known as anomalous. This strange or anomalous behavior is known as anomalous scattering. Under normal scattering, we will later prove that the intensities of the HKL reflection and H bar, K bar, L bar are the inverse or minus H, minus K, minus L reflections will be the same. That is, intensity of HKL will be equal to intensity of H bar, K bar, L bar reflections. This is known as Friedel's law. But in the case of X-ray anomalous scattering, intensity of HKL will not be equal to intensity of H bar, K bar, L bar, and this is known as violation of Friedel's law. The intensity difference I of HKL minus I of H bar, K bar, L bar, known as Bijvoet difference, has some use in crystallography. Actually, this difference is known as Bijvoet difference to honor Professor Bijvoet, who found the difference, and Professor Bijvoet was a great scientist from University of Amsterdam, the Nijmegen. Ramachandran Raman, in the year 1956 from University of Madras, Crystallography and Biophysics department, proved that the difference in intensity caused due to the presence of a heavy atom and anomalous scattering, that is the Bijvoet difference, can be made use of as a phasing technique in locating the heavy atom. In fact, during the time of Professor Ramachandran, when he was heading the department, they have fabricated an instrument to measure these Bijvoet differences, and they have reported the values they got for this delay for typical cases in the textbook on Fourier methods in crystallography edited by G. N. Ramachandran and Srinivasan. In 1956, the same year, the same idea of utilizing the Bijvoet difference for phasing the small molecules was conceived by Friedel and Bijvoet. In fact, both the parties, they have published their own results in their research journals in their respective countries. Now we are going to learn an important topic known as absolute configuration. This is the another use of the Bijvoet difference. And what do you mean by absolute configuration? A structure and its inverse, if you call it structure as S and its inverse is S bar, they lead to the same intensities. One uses only experimental intensities to arrive at a molecular structure. To avoid the mixing of inertium of, that is native and inverse structure, for a few strong reflections, the intensity of HKL and intensity of H bar, K bar, L bar are measured experimentally during the data collection. So since these values are known, the delta I Bijvoet difference using experimental values known as delta I experiment, which is equal to I HKL from experiment minus I of H bar, K bar, L bar from experiment is now known. So this is known as Bijvoet difference coming from experiment. Once you determine the three-dimensional structure of the molecule, you have the positions little j equal to 1 to n of all the atoms in the unit cell. Now, there is a formula for the structure factor FHKL as AHKL plus I times BHKL, where AHKL and BHKL are the geometrical forms of the structure factor, for which values are available. AHKL equals summation over little j equal to 1 to n Fj cos 2 pi times Hxj plus Kyj plus Lzj, and BHKL is summation over little j equal to 1 to capital N Fj sin 2 pi times Hxj plus Kyj plus Lzj, and by taking squares and adding, that is AHKL square plus BHKL square, will give you a structure factor known as mod FHKL square calculated, because this is obtained from the calculated positions. So now this structure factor can be calculated not only for HKL reflection but also for H bar, K bar, L bar reflection from the known positions. So now we have two types of intensities, that is intensity calculated for HKL and intensity calculated for the H bar, K bar, L bar reflection. Now you define the Bijvoet difference delta I calculated as I calculated for HKL minus I calculated for H bar, K bar, L bar. So now this information is also available for these strong reflections. So now we have two sets of Bijvoet difference value, one coming from experiment, another coming from calculation after getting the structure. Now for absolute configuration, irrespective of the numerical values, the sign should be same between delta I experiment and delta I calculated. Otherwise, one has to invert all the coordinates of the molecule, and this is known as determination of absolute configuration. So again, in this regard, Professor Ramachandran's group and Srinivasan has done extensive work on many small molecules, and these are all reported in the textbook on Fourier methods in crystallography. Enormous work has been carried out in the literature by the Madras group from the Department of Crystallography and Biophysics, and one can refer to the textbook by Srinivasan and Parthasarathy. Mainly, these works have been reported by the research groups of Professor Ramachandran, Professor Srinivasan and Professor S. Parthasarathy. Here, they have done extensive work on the probability distribution of Bijvoet differences, probability distribution of anomalous phase angles, and many other problems related to anomalous scattering. Let us now see what is a Patterson. You are already familiar with a Patterson function involves squares of structure factor amplitude as coefficient. In a Fourier, we use only structure factor of a HKL reflection, which is made up of an amplitude mod FHKL multiplied by the exponent e power I times the phase of the Bragg reflection. But unfortunately, the phase is not obtainable from experiment. Therefore, this Fourier synthesis cannot be computed. So this is a bottleneck or a problematic situation called phase problem in crystallography. But if you look at the Patterson function, since we are using the squares of the structure factor amplitudes which are obtainable from experiment as the intensity of Bragg reflection, there is no phase problem at all. Now, suppose instead of this square of the amplitude, if you use square of the amplitude differences, I will tell you later on what are the differences due to, that is known as a difference Patterson. There are two types of difference Patterson. One is called a dispersive difference Patterson and the other is called Bijvoet difference or anomalous difference Patterson. What do you mean by a dispersive difference Patterson? Here, the differences between the structure factors of the same reflection arise due to the change in the real part of the atomic scattering factor corrections. So this is done in the case of multi-wavelength anomalous diffraction technique, which is known as MAT technique. The other Patterson, as I told you, Bijvoet difference or anomalous difference Patterson is nothing but, if you look into the tunability, as I told you in resonance, there are some radiation sources called synchrotron radiation source where the incoming wavelength can be tuned to any value. Suppose you have a protein or macromolecule where a heavy atom like selenium is there. By tuning the incident wavelength to the absorption edges of the selenium atom, you can make the atom to behave in an anomalous way, which means that the atomic scattering factor is going to become a complex quantity. The consequence is the imaginary part correction F double prime is going to be the largest value. So at this wavelength called the peak wavelength, we talk about hundreds of differences between the intensities of HK reflection and intensity of H bar, K bar, L bar reflection, which is termed as the Bijvoet difference. So by taking the difference between mod FHKL and mod F H bar, K bar, L bar at this wavelength where the pronounced term is there for, where value is there for F double prime, now you can do a Patterson. That is known as anomalous difference Patterson. Both the dispersive difference Patterson and anomalous difference Patterson will give you the position of the heavy atom. This is done in the case of multiple anomalous diffraction, where you collect the data both at the peak wavelength and inflection wavelength point and at the remote point, where we talk about huge change in real part of the atomic scattering factor when you collect the data between the remote wavelength and the inflection point wavelength. But nowadays people use single wavelength anomalous diffraction data, where with just the anomalous difference Patterson we can locate the position of the heavy atom. Previously, in addition to this, people have been using two more wavelengths because the detector was unable to measure such a small differences. But now the detector technology has improved a lot. Even a small difference of 0.75 between intensity of HKL and intensity of H bar, K bar, L bar reflection can be measured so accurately. That is why, instead of wasting time in collecting unnecessary data, anomalous difference Patterson is used, or Bijvoet difference Patterson is used to calculate the heavy atom from which phases can be obtained, and this is the starting phase to build up the electron density. And the name of the Patterson synthesis signifies what the difference is due to, either it is dispersive difference or the Bijvoet difference. Let us again go back to the formula for anomalous scattering, namely the atomic scattering factor little f in this case becomes a complex quantity which is equal to little f naught plus little f prime plus I time little f double prime. This is given as equation 12.1. Here f naught represents the normal term of the atomic scattering factor. F prime is the correction in the real part. It's called a dispersive term, which is usually negative. And F double prime is the correction in the imaginary part. This is always positive only. So this is shown in the figure which we are going to show you next. This is called figure 12.1a. Now, when the incident wavelength is tuned or is varied, both F prime and F double prime terms will vary, and at absorption frequency of an atom contained in the molecule, F double prime becomes positive maximum and F prime becomes the most negative. So these variations of this F prime and F double prime when one approaches the absorption edge is also shown in the figure. Now we see two figures. The first figure simply denotes that both F naught and F prime are the real parts, and in the argon diagram they lie on the same line. But the f double prime imaginary component, if you look at the expression, it is I f double prime. I is nothing but e power I times pi by 2, which means that f double prime is ahead of this total real part by 90 degree. So that is why f double prime is marked with 90 degree, and total atomic scattering factor is joined by connecting the origin and the tail of the f double prime. So it is like a vectorial diagram, f naught plus f prime going along one direction added with f double prime to get f. So f will be simply square root of f naught plus f prime whole square plus f double prime whole square. If you look at the second figure, this shows the variation of the incident wavelength. What will happen when the incident wavelength is varied? We have two graphs here. So 0 is represented here in the left hand side. Above that it is positive, below that it is negative. Above the 0 we have the curve which shows the variation of f double prime term, and below this 0 origin we have the curve which shows the variation of the term f prime. We just see that whenever the incident wavelength approaches absorption edge, so we see in f double prime curve there is a peak reached, and near to that peak, if you drop a line that hits at the dip of the f prime curve, the peak point is known as peak wavelength, and the dip in the f prime curve is known as inflection point. Then we have the two remote points, left remote and right remote. So these are denoted by lambda 3 and lambda 4 respectively. So what it means is one can collect data at 4 wavelengths, lambda 1, lambda 2, lambda 3, lambda 4. That is why this is known as multi-wavelength anomalous diffraction, and at particular wavelength near to lambda 1 or lambda 1 itself, we have maximum or pronounced value for f double prime. We say that at this wavelength lambda 1, hundreds of refraction will differ in the intensities between HKL and H bar, K bar, L bar. Let us again look into this in detail in the next projection. In high energy synchrotron radiation, the tunability of wavelengths is there. So one can collect X-ray diffraction data at 2 wavelengths, one far away from the absorption edge, that is at lambda 3 or lambda 4, and the other at lambda 2 near to the absorption edge. And one notices that the structure factor amplitude mod FHKL at lambda 4 will not be equal to the structure factor amplitude FHKL at lambda 2, because at lambda 2 there is a dip at f prime curve. F prime becomes most negative at this wavelength. So if you look into the y coordinate, your f prime value will be most negative compared to the lambda 4 cutting of this f prime curve, where it will be less negative. So this means that the real part of atomic scattering factor is varying a lot, which indirectly means that it behaves at the absorption frequency, near to absorption frequency wavelength. An atom behaves like some other atom, so which we will see later again in connection with multiple isomorphous replacement technique. Now, as the incident wavelength is tuned or varied, the real part correction f prime in the atomic scattering factor varies significantly, and between the two wavelengths in the spectrum lying at the left and near to the absorption edge, as we have just seen, the intensities of the same reflection HKL will be different between the wavelength lambda 2 near to the absorption edge and lambda 4, one of the remote. Now, if you take the difference of these structure factors and use it in a Patterson means actually the square of this is used, then we can have hundreds of Bragg reflections used in the synthesis, and this Patterson can be used to find the heavy atom positions like selenium, gold, platinum, etc. Now, since you are using the differences in structure factor caused at 2 wavelengths due to the dispersive difference or due to the f prime term variation, this is known as dispersive difference Patterson. So, when we deal about module 12 on protein structure determination, further details can be seen regarding this. Also, you see that at the f double prime curve peak, that is at lambda 1, or nearly lambda by lambda k absorption wavelength equal to 1, because lambda is a variable wavelength, and you are changing lambda, so that lambda is nearly equal to lambda k, that lambda is called lambda 1. At this stage, the tuned incident wavelength is nearly equal to the kh absorption wavelength of the anomalous scatterer. Now, the Bijvoet difference becomes dominant as f double prime reaches the maximum value. So, at this wavelength nearly equal to absorption h, that is lambda is nearly equal to lambda k, which we call it as lambda 1. The intensity difference between H-scale reflection and H bar, K bar, L bar reflection will be significant, and this can be measured for hundreds of reflections, and a Patterson with the squares of these anomalous or Bijvoet difference can be calculated. Again, we will show with the real data what we mean by dispersive differences and Bijvoet differences when we deal on protein structure determination. You can see from the graph that there is a wavelength lambda 1 where the f double prime curve takes the maximum value. So this is known as peak wavelength. Okay. Now, if the peak wavelength, you just measure the intensities of the HKL reflection and the intensities of H bar, K bar, L bar reflection, eventually they will differ, because this is a violation of Friedel's law, which is happening due to the huge anomalous scattering effect. So now, because these are unequal, the differences between these structure factor amplitudes will also be unequal. So you compute mod FHKL at lambda 1 and also mod F H bar, K bar, L bar at lambda 1, then find the difference. This is used as a coefficient in the Patterson to reveal the atomic position of the heavy atom, and this Patterson is called a Bijvoet difference Patterson or anomalous difference Patterson. So we have seen the potential applications of X-ray anomalous scattering in the field of X-ray crystallography in general, and using these Patterson maps, the heavy atom peak position can be cross-checked also. We will deal more about this when we study the single wavelength anomalous diffraction technique and the multi-wavelength anomalous diffraction methods in the module dealing with protein structure determinations. Now we are going to see a beautiful derivation which is an algebraic proof for Friedel's law. So let us start with the general classical equation for structure factor of HKL reflection. F of HKL equals summation over little j equal to 1 to n atoms in the unit cell, little fj times e power 2 pi I times hxj plus kyj plus lezj. I am calling this as equation 12.2. Now, I want to get the same expression for the reflection h bar, k bar, l bar, or minus h minus k minus l. Once you substitute minus h minus k minus l in the above expression, all the negative signs are common. I can take it outside in the power of the exponent. So, f of h bar, k bar, l bar equals summation j equal to 1 to n fj times e power minus 2 pi I times hxj plus kyj plus lezj, which I am calling it as equation 12.3. Now, I want to get the complex conjugate of FHKL, which I am denoting as F star of HKL. What I mean by complex conjugate? Already I know the structure factor is a complex quantity, because if you look into equation 12.2, there is an imaginary term occurring in the exponent. Whenever I want to take the complex quantity, complex conjugate, I becomes minus I. That's the only difference. Therefore, F star of HKL is nothing but from 12.2, instead of I you put minus I. So F star HKL becomes little summation over little j equal to 1 to n fj e power minus 2 pi I times hxj plus kyj plus lezj. If you look at this new equation 12.4 with the equation 12.3 we obtained, this is same, which means that F star of HKL equals F of H bar, K bar, L bar. Now let us see what will be F star of H bar, K bar, L bar. Here we start with equation 12.3. So because the complex conjugate is needed, in that equation 12.3, I is replaced by minus I to get you simply F star of H bar, K bar, L bar equals summation equal to j equal to 1 to n fj times e power 2 pi I times hxj plus kyj plus lezj, which is simply F of HKL. This is equation 12.6. Now let us see. What is intensity of HKL? f of HKL times f star of HKL, which is nothing but square of the structure factor amplitude, that is mod FHKL square. Now, what is FHKL? Already we proved that FHKL equals f star of h bar, k bar, l bar. Also, you have proved that f star of HKL equals f of h bar, k bar, l bar. So now we see I of HKL becoming equal to f star of h bar, k bar, l bar times f of h bar, k bar, l bar, which is nothing but modulus f of h bar, k bar, l bar whole square, which is called I of h bar, k bar, l bar. So that is the proof. Now we have proved that I of HKL equals I of h bar, k bar, l bar are intensities of HKL reflection and h bar, k bar, l bar reflections are equal. This is known as Friedel's law. This will happen only when the incident wavelength or frequency is far removed from the absorption frequency of an atom present in the molecule. So whatever you have seen now as the Friedel's law, now we are going to show that in the presence of anomalous scattering, this law is going to be violated. Of course, we can give the mathematical proof also, but it's very easy to get into the graphical method proving the violation of Friedel's law. Now, what do you mean by violation of Friedel's law? Intensity of HKL is not equal to intensity of H bar, K bar, L bar. Now let us see. Take the organ diagram. Now, structure factor of reflection H is simply summation j equal to 1 to n fj e power 2 pi I h dot rj. In the case of anomalous scattering, fj is replaced by fj naught plus fj prime plus I fj double prime. So this is shown in the graph. This expression is shown, and this is equal to f naught of h plus f prime of h plus f double prime of h. We can see the expansion later. So now what I want to say is the total structure factor is now having three components: f naught of h, the total real part, then f prime of h coming through the dispersive term, the atomic scattering factor f prime, then f double prime h, this is coming through the anomalous scattering term I f double prime as the coefficient in the structure factor. So graphically, if you look at the top portion given in the graph, so now origin is there in the organ diagram. We just draw a line denoting f naught of h. Then since f prime is real, with some angle, you draw other line with another magnitude. This is f prime of h. Now, f double prime of h involves imaginary quantity I. As I told you, I is nothing but e power I pi by 2. In organ diagram, angle is also important in this position vector, structure factor amplitude graphing. Therefore, what you do is, how to distinguish this f double prime and your f prime h? F double prime is ahead of this by 90 degree. Therefore, when you mark the vectors f naught plus f prime, after f prime, put a 90 degree line and there you mark f double prime h. Now when you join origin and the end point, that is your total structure factor fh. So this is for the reflection HKL, that is positive. Now inverse reflection means you have to just project it down. If the first line f naught of h is making an angle theta with the real axis, now it has to make minus theta. Okay, that is for inverse reflection. So now again we can draw the graph down the real axis. So f naught h you can see. Now f prime, the direction is changing. F prime of h is there. With that 90 degree you are marking f double prime. Now when you join, this is the total structure factor for h bar reflection. That is h bar, k bar, l bar reflection. Now from the graph you can easily see that f of h length is shorter than f of h bar. That is, intensity f of h mod square will not be equal to mod fh naught whole square, which means that this difference in intensities between h reflection and h bar reflection, that is HKL and h bar, k bar, l bar, is caused because of the longer length in the inverse reflection compared to the shorter length in the HKL reflection corresponding to these structure factor magnitudes. Or in other words, the structure factor magnitudes will differ between h bar, k bar, l bar reflection and HKL reflection in the presence of anomalous scattering. because of which the intensity of HKL will not be equal to intensity of H bar, K bar, L bar when anomalous scatters are present, and this is known as violation of Friedel's law. So whatever we have seen in the graph, it is described in detail. F naught H, by F naught H I mean F naught of HKL. It's a reflection HKL, and this is a structure factor contribution from the real parts of the atomic scattering factor in the presence of anomalous scattering. And the second term structure factor F prime of H, by that I mean F prime of HKL, which is a contribution from the real part correction term of the anomalous scatterer. Then F double prime H is the contribution from the imaginary part of the anomalous scatterer. The total contribution to the structure factor by the light atoms and the anomalous scatterers is denoted by F of H. Now we can have an expression for F of H as summation over little j equal to 1 to n F naught j plus F prime j plus I F double prime j, because this is a new scattering factor, atomic scattering factor in the presence of anomalous scattering. This is multiplied by e power 2 pi I h dot rj. This is equation 12.10. Now, when you take summation j equal to 1 to n fj naught times e power 2 pi I h dot rj, this is called f naught of h. Then summation j equal to 1 to n little f prime of j times e power 2 pi I h dot rj, this is known as capital F prime of h. Then summation j equal to 1 to n I little f double prime of j e power 2 pi I h dot rj, that is known as f double prime of h. In f double prime of h, I is already included. So this is equation 12.11. Now f naught h is real, f prime h is also real. Only thing is f prime h coefficient is the dispersive correction term, positive term for f prime. So together they can be added as f t prime h. The total, t means total real part contribution to the structure factor. Therefore, f t prime of h plus f double prime of h equals f of h. So this is equation 12.12. So for the inverse reflection h bar, k bar, l bar, these are represented with h bar. We can prove that mod f of h will not be equal to mod f of h bar, and hence I of h, which is equal to mod f h square, will not be equal to I of h bar, which is equal to mod f h bar square. So this is called violation of Friedel's law. So for this we have used the graphical procedure because it is somewhat confusing derivation for you, is not needed. Now if mod ft prime h represents the contribution to the structure factor from the non-anomalous scatterers and also from the real part of the heavy atom scattering factors, that is why we call it a total, and if mod f double prime h represents the structure factor contribution from the anomalous scattering part of the heavy atom, then the angle between these two is called theta, and there is a formula for finding cosine of this angle. Cos theta is simply mod fhkl square minus mod fh bar k bar l bar square, the whole divided by 4 times mod capital F prime t of h times mod capital F double prime of h, which can be again abbreviated as del I, the Bijvoet difference, divided by 4 times mod f prime t of h times mod f double prime of h. This is equation 12.14. Since the above formula involves cos theta, the angle you get for the theta by making substitution at the right hand side will be having values plus or minus theta, because cos theta and cos minus theta, they have the same value. So now, knowing the position of the anomalous scatterer, say from the Patterson map, mod f double prime h can be calculated. So that is how you are calculating your cos theta. Delta I told you how to calculate delta I, the Bijvoet differences. The phase angle alpha associated with the reflection HKL can now be written as alpha equals pi by 2 plus alpha r plus or minus theta. The theta is coming from equation 12.14. Now, alpha r is the phase angle subtended by the structure factor corresponding to the light atoms. So now what I want to say is, now there is an ambiguity. The total phase is pi by 2 plus alpha r plus theta, or pi by 2 plus alpha r minus theta. So this is the ambiguity. The correct phase is the one which is closer to the heavy atom phase. So that is how people use it. The Ramachandran and Raman in 1956 from University of Madras, Crystallography and Biophysics Department, Chennai, use the above approach to solve the problem for the structure of L-lysine hydrochloride, and they used chlorine atom as the anomalous scatterer. Based on the success of the above method, many other crystallographers started using the above procedure for solving the phase problem in more complicated organic molecules. This is the most outstanding contribution of Professor G. N. Ramachandran to crystallography when he was heading the department in Chennai. And this was cited during the prestigious Evolve Prize awarded to him in the year 1999 in an article written by Professor Venkatesan in 2001. Many of us think that Professor G. N. Ramachandran has contributed only to the discovery of the triple helical structure and the famous 5-side plot called Ramachandran plot. But his outstanding contributions are there in the fundamentals of crystallography, particularly to this anomalous scattering phenomena, which can be used in the case of phasing technique. Heavy atom method is one of the earliest and successful methods of determining the three-dimensional structure of molecules using X-ray diffraction data. Whenever the crystal contains relatively a small number of heavy atoms, say 1 to 3 atoms, with good atomic number, let us say chlorine or sulfur, or with heavy atomic number, the X-ray scattering from these atoms will dominate the intensity of most of the Bragg reflections. If the electron density map is calculated with the structure amplitudes and phase angles based on the heavy atom contribution, the map would reveal peaks not only at the heavy atom positions but also peaks of smallest strengths corresponding to positions of light atoms, and this process can be repeated. The moment you know the position of the heavy atom, you already got a simple formula for the structure factor of a Bragg reflection as summation j equal to 1 to n your mod fj times e power 2 pi I into hxj plus kyj plus lezj, which can be split into two parts, a of hkl plus I times b of hkl, the geometrical form of the structure factor. Therefore, we can find the phase of the heavy atom. Tan phi of hkl is bhkl by ahkl. So, knowing the atomic positions of the heavy atom, I can calculate the a part, which is summation over j equal to 1 to n fj cos 2 pi times hxj plus kyj plus lezj, and the b part summation j equal to 1 to n fj times sin times 2 pi into hxj plus kyj plus lezj. So, knowing b part and a part, I can calculate the phase. So, this heavy atom phase is approximated to the total phase of the molecule, and you are doing the electron density calculation. The heavy atom method, whatever you have seen now, was successfully used for solving vitamin B12 by Dorothy Crowfoot Hodgkin in the year 1957. Until the power of the direct methods came to be established convincingly after 1966, the heavy atom method was the most common method used by the crystallographers. Professor G. N. Ramachandran was very curious to know during the time whether there would be other forms of Fourier synthesis which might produce the peaks of the unknown parts, that is the light atoms, in a better way. Along with his students, many new forms of Fourier synthesis have been developed by Professor G. N. Ramachandran when he was heading the Center of Advanced Study in Crystallography and Biophysics, University of Madras, Chennai. He developed a synthesis known as alpha synthesis, where the Fourier coefficients are mod f4 square times mod fc e power I alpha c. For beta synthesis, he used the Fourier coefficients as mod f4 square divided by mod fc times e power I alpha c. For gamma synthesis, the Fourier coefficients are mod f0 square e power I times alpha c. So one can refer to the famous textbook Fourier methods in crystallography, published by Very Interscience in 1970, edited by Professor Ramachandran and Srinivasan. The important finding by Ramachandran's group was that the Fourier synthesis in which the magnitudes of all the structure factors are made equal, but the correct phases are used, as well as the synthesis in which the magnitudes of the structure factors are randomly distributed with the correct phases, led to the positions of the atoms which were the same as those in the ordinary Fourier synthesis. This means that the phases really determine the structure, and the structure factor magnitudes are only of secondary importance. But unfortunately, the followers of Professor Ramachandran started working only on the probability distribution of the such effect amplitudes and not heavily on the phases. The success of the anomalous scattering for such a determination depends on the measurement of significant Bijvoet differences for a large number of reflections. The Bijvoet differences depend on the space group of the crystals, influence of the number of anomalous scatters in the unit cell, the influence of the effect of structural features such as the presence of local center of symmetry in otherwise non-center symmetric crystal, and random positional errors of the anomalously scattering atoms. Lots of research works have been carried out in the above line, particularly from Professor S. Parthasarathy's team at Crystallography and Biophysics Department, University of Madras, particularly his student professors V. Parthasarathy, Ponnuswamy, and Velmurugan and others have published reputed papers in the journal Acta Crystallographicae section A, which deals with fundamentals of crystallography. So students, now let us summarize what we have learned in this module. So we have been dealing with anomalous scattering. Whenever the frequency of the incident X-ray radiation is closer to the absorption frequency of an atom in the molecule, the atomic scattering factor of that atom, instead of being a real quantity F0, now becomes a complex quantity given by F equals F0 plus F prime plus I F double prime. This F prime is the real part correction, which is usually negative, and F double prime is the imaginary part correction, which is usually positive. We have also seen what do you mean by Friedel's law. Is nothing but intensity of the HK reflection equals to intensity of H bar, K bar, L bar reflection. Not only that, we have also seen what do you mean by violation of Friedel's law, namely intensity of HKL is not equal to intensity of H bar, K bar, L bar. Since these two intensities are not equal, there will be a difference between these two intensities, and that also we have seen. This is known as Bijvoet difference because it was only Professor Bijvoet from the University of Amsterdam, from the Netherlands, who found this difference and its use. But of course, we also told you that same time Professor G. N. Ramathandran group from Chennai also find the use of the difference in finding the phases of structures. Bijvoet difference measurements are used for determining the absolute configuration also. This also we have seen by comparing the delta I, the Bijvoet difference observed, and Bijvoet difference calculated after knowing atomic positions. Their sign should match. If not, we just invert the sign of the atomic position you obtain. So this is known as absolute configuration. So students, that's all. It's the end of the module. I thank you all.